Hello, I'm Kaustubh, and I'm going to talk about KAUCUS, Knowledge Augmented User Simulators for Training Language Model Assistants. As we all know, language models play a crucial role in natural language processing and understanding, but to achieve their full potential, they require a significant amount of interactive conversational data for fine-tuning or even distilling from a larger model. Interactive data is also crucial for exhaustive testing, for example, by red teaming, which involves testing the robustness and security of language models. Currently, most interactive data collection efforts are manual, which poses several obstacles. Firstly, the data collection process can be incredibly slow, as well as it can be hard to re-experiment and perform extensive hyperparameter tuning. Besides, manual collection can be prohibitively expensive and generally offers lesser ways to control the data distribution. One promising possibility is to use simulators, which could offer an alternative approach to interactive data collection. By using simulated environments, we can automate the generation of interactive data, reducing both time and cost. Using simulators, we can create controlled environments, ensuring consistent and reliable data collection. Besides, simulated interactions can be executed at a much faster pace than manual efforts, allowing us to collect larger volumes of data more efficiently. But all is not so hunky-dory. Many of the current simulators lack in diversity and are mostly closed domain and require rigid schemas for control and grounding. For example, relying on a knowledge base or a fixed set of handcrafted rules like user persona or specific conversational styles. While such grounding can be excellent driver to steer conversations and generate diverse data, such systems remain hard to scale due to their dependency on specific schema. Simulators should be able to scale at a pace faster than or at least closer to how fast data is produced and consumed on the internet. For example, how it's used in unsupervised pre-training settings. That is only possible if we are able to reduce intermediate schemas and directly utilize natural text freely available on the internet, but still not compromise on control. So in this work, we specifically introduce knowledge simulators to do the same. To be able to create simulators which can consume free-flowing text available at a rapid pace through two ways, through retrieval augmentation and preconditioning. We introduce a simulation framework called KAUCUS and describe how two simulators, SRAG and S-control, can be used to generate interactive data and create effective downstream assistance. So here we establish our three-stage framework and describe how we create and evaluate effective simulators. In step one, we first collect human-machine demonstration data. We then use an external retrieval system to augment the data to create training data for SRAG to be able to converse by retrieving external text during the course of a dialogue. Or we use a conversational summarizer to begin the interactions conditioned on a conversational summary to train S-control to be able to converse over any initially conditioned text. In step two, we then train simulators with the knowledge augmented data. Once trained, it can be the simulators can be subsequently used as a conversation generator for data augmentation or even in a pipeline which depends on conversational interactions like RLHF. The efficacy of the simulator can be established via intrinsic metrics measured over the interactions, as well as through extrinsic metrics measured over an assistant model trained over those interactions. So in step three, we train an assistant model and then measure conversation generated by it using an external reward or preference model. For training S-control, conversational summaries are used in reverse so that S-control can generate dialogues of any arbitrary pieces of text during inference time. So here is a sample generated summary of the given dialogue about raspberries. In step one, summaries of existing dialogues are generated. In step two, S-control is used to train the output the dialogue given a summary. So for training the simulator models, we specifically choose the helpfulness split of Anthropic and the Open Assistant dataset. As an external source of knowledge, we use the MS Marco passage ranking dataset, which is a collection of queries and documents from the Bing search engine until 2020. The passage ranking dataset is not tied to a single domain, and the passages are typically 1 to 2 sentences in length, having the potential to serve as context using a few tokens. We use BM25 as our choice of retriever and a BART Excel model fine-tuned on conversational summarization tasks. So this is how our data looks like. For S1, which is the non-knowledge augmented simulator or the vanilla simulator, we use the raw conversation as shown on the left. For SRAG, shown in the middle, notice the interaction is augmented with an MS Marco passage in green. To create such training data for training SRAG, we first use the human utterance as query and execute it against a BM25 retriever to retrieve an MS Marco passage. The top passage is then appended to the start of the user utterance. Augmented conversations are then used to train the simulator. Using the user utterance as the query during training is intended for the model to learn the condition its response to both the conversational context as well as the retrieved information. During inference, we use the last assistant utterance as the query. For S control, we prepend the summary to the conversation before training. During inference, we do not use a conversational summarizer, but random passages from the web. We now use Anthropic and Open Assistant conversations along with their knowledge augmentations to train each of the simulators from S1 to S1 control RAG. For our no simulator baseline shown by the human row, we use 8,000 conversations from Anthropic's training set. For each utterance grounded simulator, that is S1 and SRAG, we use 8,000 Anthropic conversations as triggers to generate interactions. Particularly, we utilize the complete Anthropic conversation as the starting history for both the simulator and the separately held out assistant model and allow 5 more pairs of turns of interactions to be generated. Using the simulator to generate larger context provides an opportunity to collect a larger number of context response pairs for training the downstream assistant model. For the summary control simulator, we use the conversation summaries of the 8,000 conversations and find the top 10 nearest passages from MS Marco to be used as additional summaries. We then generate 80,000 conversations of about 5 pairs of turns in length. With the given simulated data, we first compute its diversity before moving on to extrinsic evaluation. As before, we resort to using lexical diversity metrics on a random sample of 125 conversations. Note that the metrics measure the lexical diversity only on the utterances generated by the simulator interaction and not on the initial Anthropic conversation history that was fed to initiate the interaction. We find that the top two highly diverse simulators are the knowledge-based one, SRAG and S-control on all the metrics. Now, with all the simulated data, we then move on to measuring how useful the data is to train downstream assistants called A1, A0, A1 RAG, etc. For each plot, the columns indicate the two assistant models being compared. The colors in blue for each row indicate where the evaluation system prefers the left-hand side model as compared to the right-hand side. We first compare A1, that is the assistant trained on 8,000 interactions generated from S1 against A0, that is the one trained without the help of a simulator. A1 beats A0 in all 4 evaluations. The results are more prominent in fast eval and steamships evaluations. This shows that with the help of a simulator, we are able to generate more data and improve downstream assistant performance. We now compare whether an assistant model ARAG, which is trained from retrieval simulated data, benefits training. With the retrieval augmented simulator, we are able to improve downstream performance across all metrics. ARAG's interactions are preferred more often as compared to A0 as well as A1. Now here are the results of assistants trained from summary control simulators. The assistants A control and A control RAG trained from the summary control simulators are more often preferred as compared to the ones without the simulator. However, the non-retrieval counterpart, A control, is more often preferred as compared to the retrieval counterpart. So the main takeaway is that knowledge augmentation through retrieval or preconditioning can be useful to create more effective simulators that can train better downstream assistant models. Thank you. For any questions, collaborations, or just to say hi, feel free to get in touch.